Imagine trying to understand data that can take any value, like human height or the temperature of a room. How do we mathematically describe the likelihood of observing specific ranges within this continuous spectrum? Key properties of a probability density function, or PDF, are that its values are always non-negative, and the total area under its curve over all possible outcomes must equal exactly 1. These two fundamental rules ensure that the PDF provides a valid and coherent description of probability for continuous random variables. The reason these properties are so crucial lies in the very definition of probability. A probability represents the chance of an event occurring, and chances cannot be negative. Therefore, a PDF, which describes the relative likelihood of a continuous random variable taking on a given value, must always produce non-negative output. Furthermore, the certainty that an event will happen, or that some outcome from the entire possible range will occur, is always 100%, or 1. Thus, when you sum up the densities across all possible outcomes, which is what calculating the total area under the curve represents, it must always equal 1. This ensures that the PDF accounts for all possible eventualities. Understanding these properties allows us to properly calculate the probability of a continuous random variable falling within a specific range. You can think of it as finding the area under the PDF curve between 2 points, which directly gives you that probability. This is how we move from a theoretical density to a practical, interpretable probability for continuous events in real-world applications. It is important to remember that a PDF does not give you the probability of a single point occurring, as that probability for any single point in a continuous distribution is effectively 0. Instead, the value of the PDF at a specific point represents the relative likelihood or density of the random variable being near that point. This concept differentiates it from probability mass functions used for discrete variables, where individual points asterisk do have probabilities. The integral of a PDF over its entire range actually yields the cumulative distribution function, or CDF, which gives the probability that a random variable takes a value less than or equal to a given point. Ultimately, grasping these core properties of a probability density function provides the bedrock for accurately interpreting the behavior of continuous random variables in machine learning and statistics. It empowers you to quantify uncertainty, make informed predictions, and build robust models when working with data that can take on a multitude of values.